Good evening, and welcome to The Sleepy Scientist. I'm very glad you're here. Before we drift into tonight's topic, I'd love to know where in the world you're listening from. Maybe you're already tucked into bed, perhaps you're settling in after a long day, or maybe this is playing quietly somewhere in the background as the evening slowly winds down. Wherever you are tonight, I hope you're comfortable, relaxed, and ready to let your mind wander for a little while. And if you'd rather listen with your screen off, we're now uploading episodes to Spotify. The link is in the description below, so you can drift off without the glow of a screen nearby. If you enjoy these slow, peaceful explorations through science, liking the video and subscribing is a simple way to help the channel keep growing. To everyone who has already subscribed and continues to return for these sleepy little journeys, thank you. It genuinely means a lot. Tonight we're going to explore something that feels wonderfully strange at first. The idea that time itself does not pass at the same rate everywhere. Move quickly enough, travel far enough from Earth, or drift close enough to something as extreme as a black hole. And two perfectly accurate clocks can eventually disagree about how much time has passed. Which is perhaps not ideal for the clocks, but it does make the universe a little more interesting. So get comfortable, let the day fade into the background, and let's begin. Why does time move slower in space? And how did Albert Einstein discover that the universe never really had one single clock in the first place? Imagine leaving Earth aboard a spacecraft, travelling through space for a while, and then returning home to discover that you have aged ever so slightly less than the people who stayed behind. It sounds like the beginning of a science fiction story, but it is not. This difference in aging is a real, measurable consequence of modern physics. It has been observed with precision clocks, unstable particles, aircraft, satellites, and astronauts. Time does not pass at exactly the same rate for everyone, everywhere. The phrase, time moves slower in space, captures part of the idea. But it also hides something important. Simply being in space does not automatically make time slow down. The rate at which a clock accumulates time depends on two major things: how that clock is moving, and the gravitational environment through which it is travelling. The first effect is called velocity time dilation. According to Albert Einstein's special theory of relativity, a clock moving rapidly relative to another observer accumulates less elapsed time between certain events than a clock following a different path through spacetime. The faster the relative motion becomes, the larger this difference can grow. At the speeds we encounter in ordinary life, the effect is extremely small. A car, a train, or even a passenger aircraft moves far too slowly compared with the speed of light for anyone to notice relativistic time dilation without very precise instruments. But spacecraft move faster, and subatomic particles can move extraordinarily close to the speed of light. At those scales, the difference becomes measurable. There is also a second effect, known as gravitational time dilation. This comes from Albert Einstein's general theory of relativity. A clock deeper inside a gravitational field runs more slowly compared with a clock located where gravity is weaker, provided the comparison is made carefully between the two locations. So a clock on the surface of Earth runs very slightly more slowly than a clock positioned far above Earth, where the planet's gravitational influence is weaker. This creates an interesting situation for astronauts. An astronaut orbiting Earth is travelling at high speed, and that motion causes their clock to run more slowly relative to clocks on the ground. But the astronaut is also farther from Earth's surface, where gravity is slightly weaker. That causes their clock to run a little faster. The two effects compete. For astronauts in low Earth orbit, such as those aboard the International Space Station, the effect caused by their orbital speed is larger. So overall they age very slightly less than people on Earth. The difference is tiny. After months in orbit, it amounts to only a small fraction of a second. Nobody returns from the International Space Station to discover that decades have passed. Still, the principle is exactly the same one that could produce enormous differences if a spacecraft travelled close enough to the speed of light. And there is another detail that makes time dilation especially strange. Nothing feels different to the person experiencing it. An astronaut does not feel their thoughts slowing down. Their heartbeat remains normal. Their watch continues ticking once per second. Chemical reactions inside their body continue normally. Electrical signals continue travelling through their nerves. Their cells continue aging. Every local process behaves exactly as expected. This is because time dilation does not affect one particular type of clock. It affects time itself as measured along that observer's path. A mechanical clock, an atomic clock, a biological organism, and even an unstable particle all follow the same underlying physics. If one observer accumulates less time along a particular journey, every physical process travelling with that observer accumulates less time as well. That is why physicists do not regard relativistic time dilation as an illusion caused by the way light reaches our eyes. Two clocks can physically separate, follow different paths through space and time, and later be brought together again. When they are compared side by side, they can show different amounts of elapsed time. Both clocks were working correctly. Neither made a mistake. They simply followed different paths through space-time. This is where our everyday intuition begins to fail us. We naturally imagine time as something universal. Somewhere in the background, it seems as though there ought to be one enormous invisible clock ticking away for the entire universe. 1 second passes here. The same second passes on Mars. The same second passes near another star. And presumably the same second passes beside a black hole. But modern physics tells us that there is no single universal clock shared by every observer. Different observers can measure different amounts of elapsed time, depending on how they move and where they are in a gravitational field. And despite how unusual that sounds, the evidence for it is remarkably strong. Particles called muons survive their journey through Earth's atmosphere because of relativistic effects. Atomic clocks flown around the world return with measurable differences in their readings. Satellite navigation systems must constantly account for the fact that clocks in orbit do not tick at exactly the same rate as clocks on Earth. And near black holes, where gravity becomes extraordinarily strong, the differences in elapsed time can become extreme. So when we ask why time moves slower in space, the deeper question is really much more interesting. Why should motion affect time at all? Why should gravity change the rate of a clock? And why does the universe allow two observers to travel from the same beginning to the same reunion, yet experience different amounts of time in between? The answer begins with a surprisingly simple idea from Albert Einstein. Perhaps time was never universal in the first place. For most of human history, time seemed wonderfully simple. A second was a second. An hour passed at the same rate whether you were standing still, riding in a carriage, sailing across an ocean, or watching the night sky from your garden. People could disagree about where something happened or how quickly it moved, but time itself appeared to sit quietly in the background, ticking along at the same pace for everyone. That intuition became deeply embedded in classical physics. Isaac Newton treated time as something absolute. In his picture of the universe, time flowed independently of everything else. It did not care where you were, how fast you were moving, or what was happening around you. There was one universal time. The entire cosmos, in effect, shared the same invisible clock. This idea was enormously successful. Newtonian mechanics could describe falling objects, cannonballs, pendulums, machines, planetary motion, and the paths of comets with astonishing accuracy. For the kinds of speeds humans experienced in ordinary life, there was no obvious reason to question the assumption that time passed identically everywhere. If two people synchronized their clocks and then moved apart, classical physics expected those clocks to continue agreeing, provided the clocks themselves were functioning properly. Motion could change position. Motion could change speed. But motion did not change time. This picture was closely connected to what became known as Galilean relativity. named after Galileo Galilei. The basic idea is familiar even without any mathematics. Imagine standing inside a large ship moving smoothly across perfectly calm water. The windows are covered, the deck is steady, and the ship is travelling at a constant speed. You toss a ball straight upward. It falls back into your hand. You pour water into a glass. It behaves normally. You walk from one side of the cabin to the other. Nothing inside the room reveals by itself whether the ship is stationary or gliding steadily forward. The laws of mechanics work the same way in both cases. Now, imagine that you walk towards the front of the ship. Someone standing on the shore would say that your speed relative to the land is your walking speed added to the speed of the ship. If the ship moves faster, you move faster relative to the shore. If you walk towards the back, your speed relative to the shore becomes smaller. This simple addition of velocities feels completely natural because it describes almost everything we experience. A ball thrown from a moving train follows the same rule. A bird flying from a moving boat follows the same rule. A person walking along a ship follows the same rule. For centuries, there seemed to be no reason why light should behave any differently. Then, electromagnetism complicated the story. During the 19th century, James Clerk Maxwell developed a unified mathematical description of electricity and magnetism. Maxwell's equations showed that changing electric fields and changing magnetic fields could sustain one another and propagate through space as electromagnetic waves. Light, according to this theory, was one of those waves, and the equations implied a definite speed for their propagation. This raised an uncomfortable question. A wave usually travels through something. Sound travels through air. Water waves travel across water. So physicists naturally wondered what medium carried light. The proposed answer was the luminiferous ether, an invisible substance thought to fill all of space. If the ether existed, then perhaps the speed predicted by Maxwell's theory was simply the speed of light relative to that ether. Earth was moving around the sun, and the sun itself was moving through space. So as Earth travelled through the ether, scientists expected there might be something like an ether wind. Light travelling with this wind might appear to move at a slightly different speed from light travelling against it. Albert Abraham Michelson and Edward Williams Morley set out to look for this effect. Their famous experiment compared beams of light travelling along different directions before bringing them back together and examining their interference pattern. If Earth were moving through a stationary ether, the journey times of the beams were expected to differ slightly as the apparatus changed orientation. But the anticipated difference did not appear. The result became one of the most famous so-called null results in physics. It did not instantly prove that the ether was impossible, and it certainly did not produce special relativity all by itself. The story was more gradual. George Francis Fitzgerald suggested that objects might physically contract in the direction of motion through the ether. Hendrik Antoon Lorentz developed mathematical transformations that could explain why experiments failed to reveal the expected ether motion. Henri Poincaré explored the deeper principle that the laws of physics might take the same form for observers, moving uniformly relative to one another. By the beginning of the 20th century, the pieces were beginning to gather. Newtonian mechanics still worked brilliantly. Maxwell's theory of electromagnetism also worked brilliantly. Yet the two frameworks did not fit together comfortably. Classical mechanics suggested that velocity should simply add. Electromagnetism seemed to contain a special speed that refused to behave that way. Something had to give. Perhaps light needed a new explanation. Perhaps the old idea of motion needed to be revised. Or perhaps the assumption that seemed most obvious of all was the one that had been hiding the problem. Maybe space and time themselves were not as absolute as everyone had believed. That was the possibility Albert Einstein was about to take seriously. In 1905, Albert Einstein published a paper with a rather modest title on the electrodynamics of moving bodies. The ideas inside it were anything but modest. Einstein was trying to resolve a problem that had been growing steadily more uncomfortable. Newtonian mechanics described ordinary motion extraordinarily well. James Clerk Maxwell's theory described electricity, magnetism, and light extraordinarily well. But the two frameworks did not fit together neatly. Rather than adding more complicated machinery to preserve the old picture of absolute space and absolute time, Einstein reconsidered the foundations. He began with two principles. The first was that the laws of physics should take the same form for every observer moving at constant velocity. Such observers are said to occupy inertial frames. An inertial frame can be thought of as any reference system that is not accelerating. It might be a laboratory floating quietly in deep space. It could be a spacecraft travelling steadily past a planet. It might simply be an imaginary coordinate system used to describe motion. If you're travelling smoothly at constant velocity with no outside reference visible, there is no experiment you can perform entirely inside your own laboratory that reveals some hidden state of absolute motion. You're perfectly entitled to describe yourself as stationary. Another observer moving steadily relative to you is equally entitled to do the same. There is no special sign somewhere in the universe declaring which one of you is really moving. Einstein's second principle was even more surprising. Every inertial observer measures the same speed of light in a vacuum. That speed is approximately 300,000 kilometers per second. In modern physics, its exact value is fixed by definition, but the important idea is that changing your own motion does not change the speed of light you measure in the way ordinary experience might suggest. Imagine driving towards an approaching car. The two vehicles close the distance faster than either vehicle moves relative to the road. Ordinary speeds add together in the familiar classical way. Light refuses to cooperate. If you travelled rapidly towards an approaching beam of light and measured its speed, you would still obtain the same value as an observer standing still relative to you. If you raced away from that beam, you would still measure the same speed, and if the source of the light itself were moving, the result would remain the same. This sounds impossible only if space and time are assumed to behave in the old Newtonian way. If everyone must agree on the speed of light, then something else must adjust. Measurements of distance must depend on motion. Measurements of duration must depend on motion. Even judgments about whether distant events happened at the same moment must depend on motion. This was the beginning of special relativity. The word relativity can sometimes create the wrong impression. Einstein was not saying that measurements are arbitrary, that every observer can simply choose their own version of reality, or that there are no fixed rules. Quite the opposite. The theory is highly restrictive. Every inertial observer must describe physics using the same underlying laws. Every inertial observer must measure the same speed of light in a vacuum, and certain combinations of space and time remain unchanged between observers even though their separate measurements of distance and duration may differ. So special relativity does not really mean that everything is relative. Some things are relative. Some things are invariant. The remarkable part is discovering which is which. The mathematical relationships connecting these different measurements are called the Lorentz transformations, named after Hendrik Antoon Lorentz. Lorentz had developed much of the relevant mathematics, while physicists were still trying to understand how electromagnetism might fit into a universe containing an ether. Einstein gave those transformations a deeper interpretation. They were not merely mathematical corrections hiding Earth's motion through some invisible substance. They described how space and time themselves are related between observers moving relative to one another. From those relationships come several effects that initially seem separate. One is time dilation, in which moving clocks accumulate time differently. Another is length contraction, in which distances measured along the direction of motion can differ between observers. And another is the relativity of simultaneity, in which observers moving relative to one another can disagree about whether distant events occurred at the same time. These are not independent oddities placed into the theory one by one. They are all consequences of the same underlying structure. Space and time are not rigid backgrounds sitting outside physics. They participate in the way motion is measured, and yet for almost everything humans do in ordinary life, Newton's older picture still works beautifully. A person walking down a street moves extremely slowly compared with light. So does a car, so does an aircraft. Even the fastest spacecraft built by humans travel at only a tiny fraction of the speed of light. At those speeds, the relativistic corrections are so small that Newtonian mechanics remains an excellent approximation. This is why daily life never prepared us for relativity. Our instincts were shaped in a world of slow motion. We evolved among falling stones, running animals, flowing rivers, and moving clouds, not particles travelling close to 300,000 kilometers per second. At ordinary speeds, space seems fixed, and time seems universal. Only when motion becomes extreme does the deeper structure reveal itself. And one of the clearest ways to see what that structure means is to imagine something very simple. A clock made from nothing more than two mirrors and a beam of light. One of the simplest ways to understand time dilation is to imagine a clock that contains almost nothing. No gears, no springs, no hands moving around a face, just two mirrors facing one another, with a pulse of light travelling back and forth between them. This is called a light clock. Imagine that the two mirrors are fixed a short distance apart, one above the other. A pulse of light leaves the lower mirror, travels upward, reflects from the upper mirror, and returns. Each completed journey can be treated as one tick. If the clock is resting beside you, the light follows a straightforward path. It goes directly upward, directly downward, and repeats. Because the distance between the mirrors is fixed, and because light travels through a vacuum at a constant speed, each tick takes the same amount of time. So far, there is nothing especially unusual. Now imagine placing that light clock inside a spacecraft. You're sitting inside the spacecraft beside it, and the spacecraft is moving smoothly through space at a constant velocity. From your point of view, nothing changes. The mirrors remain directly above and below one another. The light still travels straight upward and downward. The clock ticks normally. Now imagine another observer watching your spacecraft move past from the outside. That observer sees something different. While the pulse of light is travelling upward towards the upper mirror, the spacecraft itself is moving sideways. So by the time the light reaches the upper mirror, that mirror has shifted forward. The light therefore cannot appear to travel straight upward from the outside observer's point of view. Instead, it follows a diagonal path. On the way back down, the lower mirror has also moved farther forward, so the returning light follows another diagonal path. Seen from outside, the pulse travels along a longer route. This creates the important part of the thought experiment. Both observers must measure the same speed of light. The person travelling with the clock measures light moving at approximately 300,000 kilometers per second. The observer watching the spacecraft pass also measures the light travelling at approximately 300,000 kilometers per second. This speed does not increase simply because the spacecraft itself is moving, but the outside observer sees the light travel a longer distance. If the light covers a longer distance while still travelling at the same speed, then the journey must take more time. The ticks of the moving light clock are therefore farther apart according to the outside observer. The clock is running more slowly. This is velocity time dilation. And the important point is that there is nothing wrong with the clock. The mirrors have not moved farther apart. The light has not mysteriously slowed down. The apparatus has not become damaged because it is travelling through space. The difference comes from the relationship between space, time, and motion. The same principle applies if the light clock is replaced by something more familiar. You could use an atomic clock. You could use a carefully designed mechanical clock. You could use a chemical reaction. You could even replace the entire clock with a living person. A heartbeat does not somehow escape relativity. Neither does the firing of nerve cells, the chemistry occurring inside the body, or the gradual biological processes associated with aging. If less time accumulates along a particular path through space-time, then every process travelling along that path accumulates less time with it. This is why the phrase moving clocks run slow can be slightly misleading. It can sound as though relativity interferes specifically with clocks. It does not. Clocks merely reveal what time is doing. The amount of time dilation depends on the speed involved. Physicists describe this using a quantity known as the Lorentz factor, named after Hendrik Antoon Lorentz. At low speeds, the Lorentz factor is extremely close to 1. That means the difference between moving and stationary clocks is tiny. A commercial aircraft might travel at something around 900 kilometers per hour. That feels fast to anyone looking out of the window, but compared with the speed of light, it is almost motionless. Relativistic time dilation still occurs, but the effect is so small that extremely precise clocks are needed to measure it. An orbiting spacecraft moves much faster. The International Space Station travels at roughly 28,000 kilometers per hour. At that speed, velocity time dilation becomes more noticeable to precision instruments, although it is still far too small for astronauts to feel. Now imagine a spacecraft travelling at half the speed of light. The effect becomes much larger. At 90% of the speed of light, it becomes larger still, and as the spacecraft moves closer and closer to the speed of light, the increase in time dilation becomes increasingly dramatic. This is not a simple relationship where twice the speed produces twice the effect. At everyday velocities, almost nothing seems to happen. Closer to the speed of light, the behaviour changes rapidly. A traveller moving at an enormous fraction of light speed could experience much less elapsed time than someone who remained behind. For the traveller, however, life would still feel completely normal. Their watch would tick normally. Their meals would cool normally. Their thoughts would arrive at their usual pace. They would not look around the spacecraft and notice everything moving in slow motion. Their own local time would remain perfectly ordinary. The difference becomes meaningful when their path is compared with someone following another route through space-time. There is also a limit hidden inside all of this. Objects with mass can approach the speed of light, but they cannot be accelerated all the way to it. As a massive object moves faster, increasing amounts of energy are required to increase its speed further. The closer it gets to the speed of light, the more extreme that energy requirement becomes. Reaching light speed would require an unlimited amount of energy, so light can travel at the speed of light because particles of light have no rest mass. A spacecraft, a planet, or a person cannot. Still, they do not need to reach that limit for the effects to become remarkable. Long before then, the simple act of moving through space begins to change how much time a journey contains. Time dilation becomes much easier to understand once we loosen our grip on another assumption that feels almost impossible to question. The assumption that there is one universal present. In everyday life, we naturally imagine that events happening far apart can still share the same moment. Something happens in London. Something happens in Tokyo. And if both occurred at exactly the same time, then surely there must be some objective cosmic sense in which they happen together. Special relativity says that this is not generally true. Two observers moving relative to one another can disagree about whether distant events happened at the same time, and both can be correct. Albert Einstein explored this idea using a simple thought experiment involving a train. Imagine a long railway carriage moving smoothly along a straight track at constant speed. At one particular instant, lightning strikes the front and rear ends of the carriage. Now imagine an observer standing beside the railway, positioned exactly halfway between the two places where the strikes occur. Light from each lightning strike travels towards this observer. If the flashes reach the observer at the same moment, and the observer knows that they were equally distant from both strike locations, then the observer concludes that the two lightning strikes happened simultaneously. For the observer beside the track, the events occurred at the same time. Now consider a second observer sitting exactly halfway along the moving train. At the moment the lightning strikes occur, this passenger is moving towards the location where the front of the train was struck, and away from the location where the rear was struck. Light from both events still travels at exactly the same speed. That is crucial. The passenger does not measure the light approaching from the front as moving faster simply because the train is travelling towards it. Nor does the light coming from behind move more slowly because the passenger is moving away. Both light signals travel at the same speed in the passenger's frame, but the passenger is moving towards one arriving flash and away from the other. As a result, the flash from the front reaches the passenger before the flash from the rear. It is tempting to stop there and say that this is only a matter of light taking different amounts of time to reach the observer. Perhaps both lightning strikes really did happen simultaneously, and the passenger simply received one image earlier. But special relativity makes a deeper statement. The passenger can account for the travel time of the light. After allowing for the known speed of light and the known distances involved in the passenger's own frame, the passenger still concludes that the two lightning strikes were not simultaneous. According to the passenger, the event at the front occurred before the event at the rear. The observer beside the track says they happened together. The passenger says they did not. Neither observer has made a measurement error. The disagreement comes from the structure of space and time itself. This is the relativity of simultaneity. To understand why this matters, it helps to think about how distant clocks are synchronized. Imagine placing one clock at each end of a very long laboratory. You want them to show the same time. One method is to send a pulse of light from the midpoint of the laboratory towards both clocks. If the clocks are equally distant from the center, the light reaches both at the same moment in the laboratory's own frame. The clocks can then be set accordingly. Another method is to exchange light signals between clocks and correct for the travel time, using the fact that light moves at the same speed in every direction. Either way, synchronizing distant clocks requires a physical procedure. It is not something that happens automatically. Once the clocks have been synchronized within one inertial frame, an observer moving relative to that frame will generally say that those same clocks are not synchronized. The moving observer will use a different network of clocks, synchronized according to their own frame. This is one of the strangest consequences of special relativity. Each inertial frame has its own valid way of assigning times to distant events, and this is closely connected to time dilation. When one observer says that another observer's moving clock runs slowly, the comparison is not as simple as looking at one isolated clock from a distance. The observer is comparing the moving clock with a whole set of synchronized clocks spread through their own frame. Another observer moving relative to that system uses a different set of simultaneous comparisons. So disagreements about clock rates and disagreements about simultaneity are not separate problems. They are parts of the same geometry. A useful way to picture this is to imagine each observer slicing space-time into layers. Each layer represents all the distant events that the observer regards as happening now. For an observer at rest relative to Earth, one particular collection of distant events belongs to the present. For an observer moving rapidly past Earth, the division is tilted differently. That observer's collection of events labelled now is not the same. Physicists sometimes describe this using a plane of simultaneity. The term sounds more complicated than the idea. It simply means an observer's particular way of dividing space-time into moments that are judged to occur together. Different states of motion produce different divisions. There is no single universal present shared by every observer. This does not usually matter when the observers are moving slowly relative to one another. At ordinary speeds, the difference is so tiny that everyone can behave as though one shared present exists. For everyday life, that approximation works perfectly well, but at speeds approaching the speed of light, the disagreement can become substantial. Events separated by enormous distances can be assigned very different times by observers moving rapidly relative to one another. That conclusion can sound philosophical, and it has certainly inspired philosophical arguments about the nature of past, present, and future. But the physics itself does not require us to settle those debates. Special relativity makes a narrower and experimentally grounded claim. There is no observer-independent definition of simultaneity for spatially separated events. Observers in relative motion may assign different times to them, while remaining fully consistent with the same physical laws. This also helps resolve one of the most famous puzzles in relativity. If two people move relative to one another, each can describe the other person's clock as running slowly. That seems symmetrical. So what happens if one of them travels away, turns around, and later returns? Who will actually be younger when they meet again? The answer depends partly on the fact that the travelling observer changes their state of motion. And when that happens, their definition of which distant events on Earth are happening now changes as well. The strange behaviour of clocks is inseparable from the strange behaviour of simultaneity. Relativity does not simply tell us that moving clocks tick differently. It tells us that motion changes how space and time fit together in the first place. A few years after Albert Einstein introduced special relativity, another physicist found a way to express its meaning in an even deeper form. His name was Hermann Minkowski. In 1908, Minkowski presented a new geometric picture in which space and time were no longer treated as completely separate things. Instead, they became parts of a single four-dimensional structure called spacetime. 3 dimensions describe where something is, 1 dimension describes when it is. Together they locate an event. An event in relativity is simply something that happens at a particular place and at a particular time. The flash of a light, the launch of a spacecraft, the arrival of a traveller, the meeting of 2 clocks. Each one can be represented as a point in space-time. Now imagine following an object not just at one instant, but throughout its entire existence. A spacecraft leaves Earth, travels outward, changes direction, and eventually returns. At every moment it occupies a different place and time. If all of those events are joined together, they form what physicists call a world line. A world line is the history of an object through space-time. A person has one, a planet has one, a particle has one. Even a clock sitting motionless on a desk traces a world line, because although it is not moving through space relative to the desk, it continues moving from one moment to the next. This gives us one of the most useful ideas in relativity: proper time. Proper time is the amount of elapsed time measured by a clock as it travels along its own world line. If you carry a watch with you throughout a journey, the time shown by that watch between departure and arrival is your proper time. And this is where the geometry becomes important. 2 travellers can begin at the same event, separate, follow different world lines, and later meet again at another event. When they reunite, their clocks may no longer agree. One might have experienced more proper time than the other. This is not a visual illusion. It is not caused by signals taking longer to arrive. And it does not disappear when the travellers stand beside one another again. Their clocks can be placed next to each other and compared directly. If they followed sufficiently different paths through space-time, they may genuinely display different amounts of elapsed time. The geometry of space-time tells us why. There is a quantity known as the space-time interval. Different inertial observers may disagree about how much spatial distance separates 2 events. They may also disagree about how much time separates them. But when space and time are combined in the correct relativistic way, the space-time interval remains the same. It is invariant. That invariant structure is what allows different observers to disagree about distance and duration without physics becoming inconsistent. A loose comparison can be made with ordinary geometry. Imagine 2 people travelling between the same pair of places. One walks directly across a field, the other takes a winding path around it. They begin together and finish together, but the lengths of their routes are different. Space-time works in a vaguely similar way, although its geometry has an important twist. In ordinary Euclidean geometry, the straight path between 2 points is the shortest. In flat space-time, for 2 events that can be connected by a slower-than-light traveller, the inertial world line between them gives the greatest amount of proper time. A traveller who departs, changes velocity, and later returns can experience less proper time than someone following the inertial path between the same departure and reunion events. That is one reason the twin paradox ultimately has a geometric solution. The twins do not simply disagree about clocks. They trace different world lines, and those world lines contain different amounts of proper time. Spacetime diagrams can help make this easier to visualize. By convention, one direction of space is usually drawn horizontally, while time is drawn vertically. A stationary object appears as a line extending mostly upward. A moving object traces a tilted line because its position changes as time passes. A beam of light follows a special diagonal direction. These diagrams should not be imagined as photographs of some hidden room containing time as a physical direction we could walk into. They are mathematical maps. Their purpose is to show how events, motion, causality, and elapsed time relate to one another. One particularly useful feature of a spacetime diagram is the light cone. Imagine a flash of light emitted from a single event. As time passes, that light spreads outward. The possible paths of the light form the boundary of a light cone. Events inside the future light cone can, in principle, be influenced by the original event because a signal travelling at or below the speed of light can reach them. Events outside it are too far away in space and too close in time for any influence to arrive without travelling faster than light. The same idea extends backwards. Events inside the past light cone are events that could have influenced the present one. This divides space-time into regions of possible and impossible causal connection. The speed of light, therefore, does more than provide a very large number for spacecraft engineers to admire from a distance. It sets the structure of cause and effect. And proper time fits naturally inside this structure. A clock does not need to ask what some distant observer thinks it is doing. It simply measures the time accumulated along its own world line. Different paths can contain different amounts. That single idea explains why fast-moving particles can survive longer in a laboratory, why clocks carried aboard aircraft can return with different readings, and why satellites in orbit do not remain perfectly synchronized with clocks on Earth. The universe does not assign one universal amount of elapsed time between every pair of events. Time belongs to paths through space-time, and once that is understood, time dilation begins to look less like a strange defect in clocks and more like a natural consequence of geometry. At the speeds of ordinary life, relativity is remarkably good at hiding. A car travelling along a motorway might move at around 100 kilometers per hour. A passenger aircraft may cruise at roughly 900 kilometers per hour. Both sound fast from a human perspective, but compared with light, they are barely moving at all. Light travels through a vacuum at approximately 300,000 kilometers every second. That enormous difference in scale is why we can spend most of our lives believing that time passes identically for everyone. Velocity time dilation is always present, but at low speeds the effect is extraordinarily small. The quantity that describes its strength is the Lorentz factor. When an object is moving slowly compared with light, the Lorentz factor is extremely close to 1. The moving clock therefore accumulates almost exactly the same amount of time as a clock that remains at rest, relative to the chosen frame. Almost exactly, not perfectly. Even a passenger aircraft experiences a measurable relativistic difference if sufficiently precise atomic clocks are used. A spacecraft in low Earth orbit makes the effect a little larger. The International Space Station moves around Earth at roughly 7.7 kilometers per second. That is many times faster than a passenger aircraft, yet it is still only a tiny fraction of light speed. The velocity time dilation experienced at that speed is therefore measurable but small. Over months in orbit, the accumulated difference amounts to only tiny fractions of a second. Particle accelerators operate in an entirely different regime. Inside machines designed to accelerate subatomic particles, particles such as electrons or protons can travel extraordinarily close to the speed of light. At those velocities, relativity is no longer a delicate correction hiding many decimal places away. It dominates the behavior. The change becomes easier to appreciate by imagining spacecraft traveling at speeds far beyond anything humans can currently achieve. Suppose a spacecraft moves at half the speed of light. its time dilation is now clearly noticeable. For roughly every hour that passes, according to an observer who regards the spacecraft as moving at that speed, only about 52 minutes of proper time accumulate aboard the spacecraft. Nothing dramatic happens inside. The difference is simply large enough that ordinary clocks could reveal it easily if such a journey were possible. Now increase the spacecraft's speed to 99% of the speed of light. The result changes enormously. For roughly 1 hour measured in the outside frame, only about 8.5 minutes of proper time pass aboard the moving spacecraft. This reveals an important feature of relativity. Time dilation does not increase in a simple straight line with speed. Doubling an already high velocity does not merely double the effect. At low speeds, increasing velocity produces only tiny changes. But as an object approaches the speed of light, the Lorentz factor rises more and more rapidly. This is why travelling at 99% of light speed is profoundly different from travelling at half of light speed. And travelling at 99.9% would be more extreme again. This can create an apparent puzzle. Imagine two observers passing one another at constant velocity. From the point of view of the first observer, the second is moving. So the first observer says that the second observer's clock runs slowly. But relativity contains no preferred state of absolute rest. The second observer is equally entitled to regard themselves as stationary, and the first observer as moving. So the second observer also says that the first observer's clock runs slowly. At first, this sounds impossible. Surely both clocks cannot be slower than each other. But the disagreement is only contradictory if both observers share the same definition of which distant events are happening at the same time. They do not. Because simultaneity is relative, each observer compares the other person's moving clock with a different collection of distant clock readings. The statement that the other clock runs slowly is therefore reciprocal during uniform relative motion. Neither observer possesses a privileged perspective. The apparent contradiction disappears once time dilation and the relativity of simultaneity are treated as parts of the same structure. There is another effect that can easily be confused with this. Suppose a spacecraft is moving away from Earth while sending a radio pulse once every second according to its onboard clock. A receiver on Earth will receive those pulses farther apart. Part of that difference comes simply from the fact that each new pulse is emitted from farther away, so it has farther to travel. Relativity adds another effect known as the relativistic Doppler effect. When a light source moves away, its received light is shifted towards lower frequencies and longer wavelengths. When it approaches, the received frequency becomes higher. This changes how quickly signals appear to arrive. But the relativistic Doppler effect and time dilation are not the same thing. Physicists can account for the changing light travel time between the source and receiver. Even after those signal delays are removed mathematically, the underlying difference in elapsed time remains. There is also a companion to time dilation called length contraction. An observer watching a fast spacecraft says that the spacecraft's moving clocks run slowly. The traveller aboard the spacecraft describes the same physics differently. In the traveller's frame, distances along the direction of motion are shorter. Suppose a distant star lies several light years away according to observers on Earth. A traveller moving rapidly towards it can measure a smaller distance between Earth and the star. So Earth observers may describe a long journey during which the traveller's clock accumulates relatively little time. The traveller instead describes the destination as being closer because of length contraction. Both calculate the same departure and arrival events. Both agree when the spacecraft reaches the star. They simply divide the intervening space and time differently. And throughout the journey, neither observer notices anything unusual locally. The traveller's clock ticks normally. The earthbound observer's clock ticks normally. Their bodies, instruments, and experiments behave normally. Relativity only becomes visible when measurements made along different paths are compared. That suggests a particularly useful experiment. Instead of leaving two observers permanently separated, allow them to begin together, travel apart, and then meet again. Now there is no need to compare distant clocks or correct for the travel time of signals. The clocks can simply be placed side by side, and when that happens, relativity makes a striking prediction. They may no longer agree. Imagine two identical twins standing together on Earth. They are the same age, their clocks are synchronized. For the moment, their paths through space-time are almost identical. Then one of them boards a spacecraft. The traveller accelerates away from Earth, crosses a large distance at very high speed, turns around, and eventually returns home. When the twins meet again, relativity predicts something remarkable. The travelling twin is younger. Not merely younger in appearance. Not younger because signals took a long time to arrive. Their body has actually experienced less elapsed time. Their heartbeat has completed fewer beats. Their cells have undergone fewer changes. Their clock has recorded fewer seconds. This is the famous twin paradox. The word paradox makes it sound as though relativity has contradicted itself, but the puzzle disappears once the two journeys are examined carefully. During the long periods when the spacecraft is moving steadily away from Earth, or steadily back towards it, the situation seems symmetrical. From Earth, the travelling twin is moving, so the earthbound twin says that the traveller's clock is running slowly. But the traveller can make the same argument. From inside the spacecraft, Earth is moving, so the traveller can describe the earthbound twin's clock as running slowly. If each twin says that the other one is aging more slowly, how can there be a definite answer when they meet again? The key is that their journeys are not actually equivalent. The earthbound twin remains approximately within one inertial frame for the duration of the experiment. The travelling twin does not. The traveller first belongs to an outbound inertial frame. Then, at the distant turning point, the spacecraft changes velocity and eventually joins a different inbound inertial frame. That change matters. Acceleration is often presented as the simple answer to the twin paradox, but that explanation needs some care. The travelling twin does accelerate while leaving Earth, turning around and eventually slowing down again. The earthbound twin does not undergo the same sequence, so acceleration clearly identifies which traveller changes frames. But the age difference is not simply caused by the physical sensation of acceleration. The turnaround could be made extremely brief. The spacecraft could spend years travelling at almost constant speed, then reverse direction rapidly. Even if the period of acceleration occupies only a tiny fraction of the entire journey, the final difference in age remains. The cleanest explanation comes from proper time. Each twin follows a different world line through space-time. The earthbound twin follows one path between the departure event and the reunion event. The travelling twin follows another. Those paths contain different amounts of proper time. In flat space-time, the inertial path between two fixed events contains the greatest proper time. The traveller's path includes a departure and return, and therefore differs from that nearly inertial path. As a result, less proper time accumulates for the travelling twin. A simple example makes the effect easier to see. Suppose a distant star lies 8 light-years away according to observers on Earth. Imagine the travelling twin makes the outward journey at 80% of the speed of light, turns around and returns at the same speed. Ignoring the periods of acceleration, people on Earth would say that the journey takes about 20 years, 10 years outward, 10 years back. At 80% of the speed of light, the Lorentz factor is about 1.67. That means the traveller experiences only about 12 years during the same journey. When the twins reunite, one has aged roughly 20 years. The other has aged roughly 12. Both clocks worked perfectly. Both twins felt completely normal throughout their own local experience. The difference comes from the geometry of their paths. The travelling twin can also describe the entire situation consistently. During the outward journey, the traveller says that Earth is moving away and that clocks on Earth are running slowly. During the return journey, the traveller again says that Earth is moving and its clocks are running slowly. The important change happens when the traveller switches from the outbound frame to the inbound frame. Because simultaneity is relative, Changing inertial frames changes which distant events on Earth the traveller regards as happening now. Before the turnaround, one set of Earth events is considered simultaneous with the traveller's present moment. After the turnaround, a different set is. In the traveller's coordinate description, the assigned time on distant Earth advances sharply during this change of frame. That does not mean the traveller literally watches Earth suddenly race through several years in a single instant. What is received through a telescope is a separate issue. Actual images and radio signals are affected by the time light takes to cross the distance. While the spacecraft is moving away, signals from Earth arrive less frequently. Each new message must travel farther to catch the receding traveller. The relativistic Doppler effect stretches those signals further. Earth therefore appears to be evolving slowly. Once the spacecraft turns around and begins travelling home, the situation reverses. Signals sent from Earth are now encountered more rapidly. Their received frequency increases. Earth appears to age more quickly. The visual experience is smooth. There is no magical moment when years suddenly flash past before the traveller's eyes. But if both twins carefully account for signal travel times and their changing states of motion, they calculate the same final result. Radio messages provide a particularly intuitive way to imagine this. Suppose each twin sends the other one a message every birthday. During the outward journey, the traveller receives Earth's birthday messages at a reduced rate. The Earthbound twin likewise receives the traveller's messages slowly. After the spacecraft turns around, messages begin arriving at a faster rate because the distance between sender and receiver is shrinking. When all the signals are collected and the twins finally reunite, there is no disagreement about the total number of birthdays each person has experienced. One has simply lived through fewer of them. The Earthbound twin is not perfectly inertial in the strictest physical sense. Earth rotates once each day. It travels around the Sun. The solar system moves through the Milky Way. And Earth's gravity means that the full situation is ultimately described by general relativity rather than perfectly flat spacetime. But none of this rescues the symmetry of the twins. A more complete calculation can include Earth's motion, gravity, and every period of acceleration. The result remains the same in principle. Different world lines can accumulate different amounts of proper time, and the twin paradox is no longer merely a thought experiment. Its ingredients have been tested repeatedly. Atomic clocks have been carried aboard aircraft, and later compared with clocks that remained on the ground. Clocks aboard satellites accumulate time differently from clocks on Earth. Unstable particles moving at relativistic speed survive for longer laboratory times than identical particles at rest. Precision measurements repeatedly show that elapsed time depends on the path taken through space-time. The human version of the twin experiment remains far beyond our technology because we cannot send people across interstellar distances at anything close to the speed of light. But the physics itself is already familiar. A moving particle can be our travelling twin. An atomic clock can be our travelling twin. A satellite can be our travelling twin. Separate them from another clock. Allow them to follow different paths. Bring them back together. Then compare. Relativity does not leave the answer vague. The clocks remember the geometry of the journeys they have taken. High above us, particles are constantly arriving from space. Most never reach the ground in their original form. Instead, they collide with the atmosphere and create cascades of new particles, some of which survive long enough to pass through buildings, rocks, and even our own bodies. Among them are particles called muons. A muon is an elementary particle closely related to the electron. It carries the same electric charge as an electron, but it is roughly 200 times more massive. There is also one particularly useful difference. Muons are unstable. Left alone, a muon survives for an average of only about 2.2 millionths of a second before decaying into other particles. That extremely short lifetime makes muons remarkably useful tests of relativity. Many of the muons passing through Earth are created indirectly by cosmic rays. Cosmic rays are high-energy particles arriving from space, most commonly protons and atomic nuclei. When one of these particles crashes into the nucleus of an atom high in Earth's atmosphere, the collision can produce a shower of secondary particles. Among those particles are unstable particles called pions and kaons. These can decay to produce muons, which then continue travelling downward towards Earth's surface. The atmosphere above them is still many kilometres thick, and that creates a problem if we try to understand their journey using classical physics alone. A muon survives for only about 2.2 millionths of a second on average. Even if it travelled almost as fast as light during that entire lifetime, classical reasoning would suggest that it could cover only around 660 metres before decaying. That is a respectable distance for something that exists for only a few millionths of a second, but it is nowhere near enough. Atmospheric muons are commonly produced many kilometres above sea level, often at altitudes around 10 to 15 kilometres. If their lifetimes behaved according to simple classical expectations, the overwhelming majority should disappear long before reaching detectors on the ground. Yet muons arrive at Earth's surface in enormous numbers. At sea level, roughly 1 muon passes through each square centimetre of horizontal area every minute, although the exact rate depends on direction, altitude, and energy. A person sitting quietly at home is therefore being crossed by muons all the time. Fortunately, they usually pass through without introducing themselves. Their ability to reach us is a direct consequence of relativity. From the perspective of an observer on Earth, the muons are moving at speeds extremely close to the speed of light. Their internal decay process therefore undergoes velocity time dilation. The muon still has the same average lifetime in its own rest frame, but according to the Earthbound laboratory frame, its decay proceeds more slowly. A sufficiently energetic muon can therefore survive for many times 2.2 millionths of a second as measured on Earth. That gives it enough laboratory time to travel through kilometres of atmosphere before decaying. The faster the muon moves, the larger its Lorentz factor becomes, and the longer its lifetime appears in the Earth frame. For a muon moving at more than 99% of the speed of light, the effect can be substantial. So Earthbound observers have a straightforward explanation. The moving muon experiences time dilation. Its clock runs slowly relative to clocks on Earth, allowing it to travel much farther than a classical calculation would predict. But the muon itself cannot describe its own time as running slowly. In the muon's frame, its average lifetime remains approximately 2.2 millionths of a second. Nothing unusual happens to its decay. Instead, relativity changes something else. The atmosphere becomes shorter. Because Earth and its atmosphere are moving rapidly towards the muon in this frame, the distance along the direction of a motion is reduced by length contraction. A layer of atmosphere that might measure many kilometres thick in Earth's frame can be dramatically contracted in the muon's frame. So the muon has only a much shorter distance to cross before reaching the surface. The Earth observer says the muon survives longer. The muon's frame says the journey is shorter. Both descriptions predict the same result, and both arise from exactly the same special theory of relativity. Muon observations became important tests of these ideas during the 20th century. In 1941, physicists Bruno Rossi and David Hall studied cosmic ray particles at different altitudes. They compared the numbers of rapidly moving unstable particles detected higher up with the number surviving farther down. The survival rates were consistent with the increased laboratory lifetimes predicted by special relativity. A particularly memorable demonstration was performed in 1963 by David Frisch and James Smith. They measured muons near the summit of Mount Washington in New Hampshire and considered how many should survive the journey to a much lower altitude. Without relativistic time dilation, very few of the detected muons should have lasted long enough to complete the descent. Instead, many more survived. When the relativistic correction was included, the prediction agreed far better with the observations. The beauty of muons is that they remove one possible misunderstanding about relativistic clocks. A mechanical clock could always invite suspicion. Perhaps moving very quickly shakes the mechanism. Perhaps the gears behave differently. Perhaps an atomic clock is somehow being disturbed by its environment. A muon has no clockwork hidden inside it. Its decay is an intrinsic quantum process, yet its measured lifetime changes with its motion in exactly the way relativity predicts. Time dilation, therefore, cannot reasonably be dismissed as something happening only to particular kinds of clocks. The entire physical process follows the altered amount of elapsed time. Of course, atmospheric muons are not a single experiment that somehow proves all of relativity on their own. Science rarely works so neatly. Instead, muon survival forms one part of a much larger network of evidence. Time dilation agrees with observations of atomic clocks, satellite systems, astrophysical phenomena, and many different types of unstable particles. And modern particle accelerators allow the idea to be tested under far more controlled conditions. There, scientists can create particles deliberately, measure their energies, determine their velocities, track the distances they travel, and record where they decay. The atmosphere provides a natural particle accelerator above our heads. Laboratories allow us to repeat the experiment more carefully. In both places, the lesson is the same. A particle that lives for only a few millionths of a second can cross kilometers of space, not because it has somehow learned to postpone its decay, but because motion changes the amount of time that passes along its path. Particle accelerators provide one of the clearest places to see relativity operating under controlled conditions. Instead of waiting for cosmic rays to strike the atmosphere and produce particles by chance, scientists can create beams of charged particles, accelerate them deliberately, guide them through carefully designed paths, and measure how they behave. At the European Organization for Nuclear Research near Geneva, enormous accelerator systems push particles to speeds extraordinarily close to the speed of light. At those velocities, relativity is not a minor correction. It becomes essential. Scientists need relativistic calculations to predict particle energies, momenta, trajectories, collision times, and the distances unstable particles are likely to travel before decaying. Without those corrections, the entire experiment would quickly stop making sense. One of the most important things to understand is what happens as a particle is given more and more energy. At low speeds, adding energy produces a noticeable increase in velocity. Push something harder, and it moves faster. But as a particle approaches the speed of light, that familiar relationship begins to change. Its speed can still increase, but only by smaller and smaller amounts. The particle may already be travelling at more than 99% of the speed of light, and adding enormous amounts of additional energy will barely change that speed. The extra energy instead appears primarily as greater relativistic energy and momentum. This is why physicists generally avoid the older explanation that a particle's mass simply increases as it moves faster. Modern treatments keep the particle's rest mass, also called invariant mass, fixed. What changes dramatically with velocity are its energy and momentum. This distinction matters because it provides a much cleaner description of what accelerator experiments actually measure. A proton moving slowly and a proton moving close to the speed of light are still the same kind of particle, with the same invariant rest mass. But the high-speed proton can carry vastly more energy and momentum. At the European Organization for Nuclear Research, protons accelerated in large machines can move so close to light speed that the difference becomes almost difficult to express intuitively. They never quite reach the speed of light, but they can approach it extremely closely, and unstable particles created in accelerator experiments reveal the consequences immediately. Suppose a short-lived particle would normally survive for only a tiny fraction of a second in its own rest frame. If that particle is moving rapidly through a detector, then observers in the laboratory measure its internal clock as running more slowly. Its average laboratory lifetime becomes longer. That allows the particle to travel farther before decaying. This is the same principle that allows atmospheric muons to reach Earth's surface. The difference is that inside an accelerator, the conditions can be controlled far more precisely. Scientists can measure the particle's energy. They can determine its momentum. They can reconstruct its trajectory. And they can observe where it decays. One particularly important test involved muons circulating in a storage ring at the European Organization for Nuclear Research. In 1977, a team led by John Bailey studied muons moving at relativistic speeds around a circular path. The muons were travelling so quickly that special relativity predicted a large increase in their measured lifetime compared with muons at rest. The experiment found exactly that. From the perspective of the laboratory, the circulating muons survived for much longer than their ordinary rest frame lifetime of around 2.2 millionths of a second. Their decay rates matched the relativistic prediction. The circular path makes the experiment especially interesting. A muon travelling around a storage ring is not moving in a straight line at constant velocity. Its direction is continually changing. That means the particle is accelerating. Strong magnetic fields are used to bend the trajectories of charged particles and keep them circulating around the ring, but the presence of acceleration does not somehow switch off velocity time dilation. The muon still accumulates proper time according to its path through spacetime, and when researchers compare its measured lifetime with what relativity predicts, the agreement remains extremely strong. Circular motion does require more careful treatment than simple straight-line motion. The particle repeatedly changes direction, and its frame is not one single inertial frame throughout the journey. But the underlying principle remains intact. The amount of proper time accumulated along the muons world line determines how much aging, or in this case how much decay, takes place. This has allowed accelerator experiments to test relativity in ways that simple thought experiments cannot. Researchers can look for possible changes related to direction. They can test particles moving at different energies. They can compare different particle species. They can study particles undergoing substantial acceleration. And they can examine whether decay rates behave as relativity predicts under all of those conditions. Again and again, the results have been consistent with the relativistic framework. This matters enormously for particle detectors. When particles collide inside a modern accelerator, the resulting event may produce many short-lived particles. Some survive only briefly before decaying into other particles. The distance between the collision point and the location of a later decay can reveal the particle's lifetime and help identify what was created. If relativistic time dilation were ignored, scientists would often predict decay distances that were completely wrong. A particle expected to disappear almost immediately could instead travel a measurable distance through the detector. Its decay products might appear centimeters, meters, or farther from the point where the particle was created, depending on its lifetime and speed. Detector designs, reconstruction software, and particle identification all have to account for this. Relativity is therefore not simply a philosophical interpretation placed on top of accelerator physics. It is built into the machinery. It is built into the calculations used to steer the beams. It is built into the expected energies and momenta. It is built into the timing of collisions, and it is built into the interpretation of what happens after those collisions occur. Modern high-energy physics would not function properly if time dilation were merely an illusion caused by observation. The particles behave as though the elapsed time along their paths is genuinely different. A muon does not possess a wristwatch. It simply decays according to the proper time it experiences. That makes particle accelerators extraordinarily precise laboratories for testing Einstein's description of motion. But particles are still very distant from everyday intuition. It is one thing to say that a muon survives longer while racing around a storage ring. It is another to take two clocks made by humans, synchronize them carefully, send one on a journey, and then bring them back together. At that point, relativity can be read directly from the clocks themselves. For most of history, clocks were limited by the things they were made from. Pendulums swing, springs unwind, gears turn. All of them can be remarkably accurate, but they are still mechanical systems vulnerable to temperature, vibration, friction, and tiny imperfections in construction. Atomic clocks work very differently. Instead of relying on a swinging pendulum or a rotating wheel, they measure time using extremely stable transitions associated with atoms. Atoms can absorb or emit electromagnetic radiation at very specific frequencies when they move between particular energy states. Those frequencies are extraordinarily consistent. And because identical atoms behave in the same way wherever the laws of physics are the same, they provide something close to a natural reference for measuring time. One of the most important examples uses the cesium-133 atom. The modern definition of the second is based on a particular transition associated with cesium-133. 1 second corresponds to 9,192,631,770 periods of the radiation associated with that transition. It is an impressively complicated way of saying that we have chosen an extremely reliable atomic rhythm and agreed to call a certain number of its cycles 1 second. This precision makes atomic clocks wonderful tools for relativity. It does not make them immune to relativity. In fact, the opposite is true. Because they are so precise, atomic clocks reveal differences in elapsed time that would be impossible to notice with ordinary mechanical clocks. This was demonstrated dramatically in 1971 by physicists Joseph Haffel and Richard Keating. They took portable cesium atomic clocks aboard commercial aircraft and flew them around the world. Some of the clocks travelled eastward, others travelled westward. Meanwhile, reference clocks remained behind at the United States Naval Observatory. Once the journeys were complete, the travelling clocks were brought back and compared directly with the clocks that had stayed on the ground. Relativity predicted that they should no longer agree exactly, but the prediction was more complicated than simply saying that the moving clock should lose time. Two different relativistic effects were acting at once. The first came from special relativity. Because the aircraft were moving relative to an appropriate reference frame, their motion produced velocity time dilation. Motion tends to reduce the amount of proper time accumulated by a moving clock. The second effect came from general relativity. The aircraft were flying several kilometers above Earth's surface, where Earth's gravitational field is slightly weaker. A clock higher in a gravitational field tends to run faster than an otherwise identical clock lower down. So one effect pushed the airborne clocks slightly slower, the other pushed them slightly faster. Then Earth's rotation made things more interesting. The planet is already spinning from west to east. An aircraft flying eastward moves in the same general direction as Earth's rotation, relative to a suitable non-rotating frame centered approximately on Earth, that increases its overall speed. An aircraft flying westward does the opposite. Its motion partly cancels the rotational motion of Earth beneath it, so the eastward and westward clocks were not expected to experience identical velocity time dilation. The predictions were different. When Haffel and Keating compared the clocks after their journeys, the measured differences were broadly consistent with the combined effects predicted by special and general relativity. The eastward clocks lost time relative to the reference clocks. The westward clocks gained time. The measured changes were extremely small, counted in billionths of a second. Yet they were large enough for cesium atomic clocks to detect. The experiment became one of the best-known demonstrations that moving clocks and clocks at different heights accumulate different amounts of time. It is worth keeping the result in perspective. The original experiment had significant experimental uncertainties, and later researchers have examined aspects of the measurements and analysis in detail. Relativity does not stand or fall on one set of clocks carried aboard commercial aircraft in the early 1970s. Since then, far more precise tests have been performed. Atomic clocks have travelled aboard aircraft, rockets, and satellites. Others have been compared between laboratories at different altitudes. Modern experiments can measure differences far smaller than those available to Haffel and Keating. The clocks themselves have also improved enormously. Traditional cesium clocks operate using microwave frequencies. Modern optical clocks use much higher frequencies associated with transitions in atoms or ions. Because these oscillations occur so rapidly, optical clocks can divide time into much finer intervals. Some of the best modern clocks are so stable that they can detect relativistic effects caused by surprisingly small differences in height. Move one precision clock slightly higher than another, and the difference in gravitational potential can alter their relative ticking rates. The effect is tiny, but with sufficiently advanced optical clocks, even differences across a room or between floors of a building can become measurable. A clock placed higher above Earth experiences slightly less gravitational time dilation and therefore runs slightly faster than one lower down. That statement may sound almost absurdly delicate. Raise a clock, wait, and the universe gives it a tiny amount of extra time. But this is now within reach of laboratory measurement. The precision has become so extraordinary that clocks can also be used to investigate Earth itself. This has led to a field known as relativistic geodesy. Traditional geodesy measures the shape of Earth, its gravitational field, and the heights of locations on its surface. Relativistic geodesy adds another tool. Because clock rates depend on gravitational potential, comparing extremely precise clocks at different locations can reveal differences in that potential. In principle, clocks can help determine differences in height and changes in Earth's gravitational environment, so timekeeping becomes a way of mapping gravity. This leads directly into Albert Einstein's broader theory. Special relativity explains why motion affects elapsed time, but the aircraft experiments also show that changing altitude matters even when two clocks are moving only modestly relative to one another. A clock does not need to race close to the speed of light to experience a different amount of time. It can simply be placed higher. Gravity changes the comparison. And once that is understood, the idea that time moves differently in space becomes more subtle. Sometimes motion makes a clock run slower. Sometimes weaker gravity makes it run faster. And in the real universe, both effects are often happening at once. Special relativity changed our understanding of motion, distance, and time. But it had an important limitation. It dealt most directly with observers moving at constant velocity through flat space-time. It could explain why fast-moving clocks run slowly, and why different observers disagree about simultaneity, but it did not yet provide a complete description of gravity. Albert Einstein spent years trying to extend the same deeper logic to accelerated motion and gravitational fields. The result was the general theory of relativity, completed in 1915. At its heart was an idea that Einstein had been developing for years: the equivalence principle. Imagine standing inside a completely enclosed lift. There are no windows. You cannot see outside. If the lift is standing still on the surface of Earth, you feel your feet pressed against the floor because gravity is holding you there. Now imagine the same lift far away from planets and stars floating in deep space. If a rocket engine beneath it begins accelerating upward, you again feel pressed against the floor. Drop an object from your hand, and it appears to fall towards your feet. From inside the lift alone, the two situations can look remarkably similar. One involves gravity, the other involves acceleration. Einstein realized that this similarity was not a coincidence. Locally, the effects of a uniform gravitational field and the effects of acceleration can be equivalent. That insight opened the way to a completely different description of gravity. In Isaac Newton's picture, gravity is a force acting between masses. Earth pulls on the moon, the sun pulls on Earth. A falling apple is pulled towards the ground. General relativity changes the underlying explanation. Matter and energy alter the geometry of space-time. Objects then move through that curved space-time along the most natural paths available to them. These paths are called geodesics. A geodesic is the closest equivalent in curved space-time to a straight line through ordinary flat space. An object in free fall follows one. So an astronaut orbiting Earth is not being continuously held up against gravity. The astronaut and the spacecraft are both freely falling along geodesics through curved space-time. They remain in orbit because their forward motion and the geometry around Earth combine to produce a path that continually curves around the planet. This description applies to light as well. Light has no rest mass, yet its path is still affected by curved space-time. That is why massive objects such as stars and galaxies can bend light passing nearby. but it is easy to oversimplify this and say that mass merely curves space. General relativity is about space-time. Time is part of the geometry too, and for many familiar gravitational effects, the behaviour of time is not a small detail, it is central. Einstein's field equations describe how mass, energy, momentum, and pressure influence space-time geometry. That geometry then determines how matter and light move. The usual summary is that matter tells space-time how to curve, and curved space-time tells matter how to move. It is a useful phrase, although the full theory is more precise than the slogan. The connection between gravity and time can be understood using another version of Einstein's accelerating lift. Imagine a tall spacecraft accelerating upward through otherwise empty space. Place one clock near the floor and another near the ceiling. Now imagine the lower clock sending a beam of light upward towards the upper clock. While that light is travelling, the entire spacecraft continues accelerating. By the time the signal reaches the ceiling, the upper clock is moving slightly faster than it was when the light was emitted. The receiver therefore measures the light at a different frequency. From the viewpoint of the accelerating spacecraft, light sent upward is shifted towards a lower frequency. Now use the equivalence principle. If acceleration and gravity are locally equivalent, then a similar effect should occur when light climbs through a gravitational field. Light travelling upward away from a massive body is observed at a lower frequency. This is gravitational redshift. Light travelling downward to a lower gravitational potential is observed at a higher frequency, producing a gravitational blue shift. The effect is directly connected to time. Suppose the light is produced by an atom undergoing a very specific transition. That transition can function as a clock. If identical atomic processes at two different heights are observed to operate at different relative frequencies, then the clocks based on those processes cannot be accumulating time at exactly the same rate. A clock lower in a gravitational field runs more slowly relative to one higher up. This is gravitational time dilation. It means that a clock on Earth's surface accumulates slightly less time than an otherwise identical clock located high above the planet. The difference is tiny in Earth's relatively weak gravitational field, but it is real, and unlike velocity time dilation, it does not require the two clocks to be racing past one another at enormous speed. They can remain nearly stationary relative to each other. Simply placing them at different gravitational potentials is enough. Locally, however, nothing seems strange. Imagine falling freely inside a small laboratory. For a sufficiently small region of space, and a sufficiently short period of time, you can treat that laboratory as though gravity has disappeared. Objects float beside you. Experiments behave according to special relativity. This is why general relativity preserves special relativity locally. Curved space-time may behave very differently across large distances, but within a small enough freely falling region, it looks approximately flat. So the familiar phrase gravity slows time is useful, but it is not quite the deepest description. Gravity is not reaching into a clock and forcing its mechanism to move more slowly. Different paths through curved space-time contain different amounts of proper time. A clock near Earth, a clock on a mountain, a clock aboard a satellite, a clock falling towards a black hole. Each follows its own world line through a space-time whose geometry has been shaped by matter and energy. And the amount of time accumulated along those paths does not have to be the same. One of the earliest practical ways to test general relativity was to look very carefully at light. If gravity changes the rate at which clocks run, then light travelling between different heights in a gravitational field should carry evidence of that difference. This effect is known as gravitational redshift. Imagine a photon travelling upward, away from Earth. An observer higher in the gravitational field receives that photon at a slightly lower frequency than an observer located closer to where it was emitted. Lower frequency means a longer wavelength, so the light appears shifted very slightly towards the red end of the spectrum. Near Earth, the effect is extremely small, but general relativity predicts it precisely. A common way to describe what happens is to say that the photon loses energy as it climbs out of a gravitational field. That picture can be useful in simple situations, especially in weak gravitational fields such as the one around Earth, but it is not the deepest description. In curved space-time, energy cannot always be treated as a single global quantity in quite the same straightforward way as it can in ordinary flat space-time. The more precise statement is that observers located at different gravitational potentials measure different frequencies for the same travelling light signal, and because frequency can be used to keep time, gravitational redshift is closely tied to gravitational time dilation. A major experimental test came in 1959. At Harvard University, Robert Pound and Glenn Rebka designed an experiment to measure the tiny change in frequency experienced by gamma rays travelling vertically through Earth's gravitational field. The vertical distance involved was only about 22 meters. That is not exactly a grand journey through the cosmos. It is closer to moving between different floors of a building. Yet even across that small difference in height, general relativity predicted a measurable shift. The difficulty was that the shift was extraordinarily tiny. To detect it, Pound and Rebka relied on the Mössbauer effect, discovered by Rudolf Mössbauer. Normally, when an atomic nucleus emits a gamma ray, the nucleus recoils slightly. That recoil changes the energy of the emitted photon and broadens the range of energies involved. The same problem appears when another nucleus absorbs the gamma ray. This makes extremely fine measurements difficult. The Mössbauer effect allows certain nuclei locked inside a solid crystal to emit and absorb gamma rays with almost no individual recoil. Instead, the surrounding crystal takes up the momentum collectively. That produces extremely sharp resonance lines, and those very precise resonance frequencies made it possible to detect the tiny gravitational shift. Pound and Rebka compared gamma rays travelling between different heights inside a tower. Because the gravitational effect was so small, they also moved the source, or absorber, very slightly to create a controlled Doppler shift. By adjusting that motion until the gamma rays were once again absorbed efficiently, they could determine how much gravitational redshift had occurred. Their result agreed with general relativity within the precision available at the time. Later experiments improved on the measurement. Joseph Snyder worked with Robert Pound on follow-up tests that achieved greater accuracy and provided stronger confirmation of gravitational redshift. These experiments mattered because they connected gravity directly with measurable changes in frequency, and frequency is intimately connected with time. If identical atomic processes at different heights produce signals that are measured at different rates, then clocks based on those processes not accumulating time identically. A much more ambitious test came in 1976. The mission was called Gravity Probe A. Robert Vessott and Martin Levine were among the scientists involved. A highly stable hydrogen maser clock was carried aboard a rocket to an altitude of roughly 10,000 kilometers above Earth. A hydrogen maser measures time using a very stable microwave transition associated with hydrogen atoms. As the rocket climbed higher, it moved farther out of Earth's gravitational well. General relativity predicted that the clock aboard the rocket should run faster relative to clocks remaining on Earth. Radio signals from the spaceborne clock were transmitted back and compared with reference clocks on the ground. The experiment measured the gravitational frequency shift to very high precision. Once again, the result matched the prediction of general relativity closely. By this point, gravitational time dilation was no longer something confined to calculations about stars or black holes. It could be measured around Earth itself. Modern atomic clocks have pushed this much further. Two highly precise clocks placed at different elevations will not tick at exactly the same rate. A clock on a mountain runs slightly faster than an otherwise identical clock near sea level. The reason is that the mountain clock sits at a higher gravitational potential. It is farther out of Earth's gravitational well. The difference is tiny. Near Earth's surface, raising a clock by about 1 meter changes its rate by roughly 1 part in 10 to the power of 16. That corresponds to an accumulated difference of only a few billionths of a second over many months. For ordinary life, that is completely irrelevant. For modern precision clocks, it is measurable. Optical clocks are especially powerful. Instead of using microwave transitions, they use much higher frequency transitions associated with atoms or ions. That higher frequency provides a much finer division of time. Some optical clocks are sensitive enough to detect gravitational time differences caused by surprisingly small changes in height. Move one clock upward within a laboratory, and given sufficient precision, it can be made to tick measurably faster than another clock below it. This gives timekeeping an unusual new role. Clocks can help measure gravity. The idea has developed into relativistic geodesy. Traditional geodesy measures the shape of Earth, its gravitational field, and the elevation of different locations. Relativistic geodesy uses differences in clock rates to help determine gravitational potential. Two clocks placed at different locations can reveal something about the height and gravitational environment of those locations simply by comparing how quickly they accumulate time. This also reveals an important distinction. Gravitational time dilation depends primarily on gravitational potential, not simply on how strong the local gravitational force feels. Those are not the same thing. A person in orbit can feel weightless even while still being deeply inside Earth's gravitational influence. Astronauts aboard an orbiting spacecraft are not beyond gravity. They are in continuous free fall around Earth. The local sensation of weight may disappear, but the gravitational environment still affects the relationship between their clock and clocks elsewhere. This is one reason the phrase "gravity slows time" must be used carefully. A clock lower in a gravitational potential runs more slowly relative to a clock higher up. Move a clock away from Earth, and gravitational time dilation becomes weaker. That means the clock tends to run faster relative to one remaining on the surface. And this creates an important correction to the simple idea that time always moves slower in space. Travelling upward can actually make a clock run faster. Of course, a spacecraft usually moves rapidly as well. Its velocity then introduces special relativistic time dilation, which pushes in the opposite direction. So a real clock in space is often caught between two effects. Its speed tends to slow it down. Its greater distance from Earth tends to speed it up. Which effect wins depends on the orbit, the altitude, the velocity, and the clock chosen for comparison. The further we move from simple examples, the clearer the lesson becomes. Space itself does not slow time. Gravity does not slow every clock by the same amount. Motion does not affect every observer in one universal way. Elapsed time depends on the path a clock follows through space-time, and once gravity and motion are both included, the simple phrase "time moves slower in space" becomes far more interesting than it first appears. The phrase "time moves slower in space" sounds simple. It is also only partly true. Empty space does not possess some universal property that slows every clock placed inside it. A clock does not leave Earth, cross an invisible boundary, and suddenly begin running more slowly simply because there is black sky outside the window. The real situation is more interesting. Two different effects are usually competing. The first is velocity time dilation. The faster a clock moves relative to a chosen observer, the less proper time it accumulates along its path. The second is gravitational time dilation. The deeper a clock sits inside a gravitational field, the more slowly it runs relative to a clock located at a higher gravitational potential. So when a spacecraft leaves Earth, both effects can appear at once. Its increasing speed tends to make its clock run more slowly. Its increasing altitude tends to make the clock run faster, because it is moving farther out of Earth's gravitational well. Which effect is larger depends on the details. Altitude matters, velocity matters, the trajectory matters, and just as importantly, the answer depends on which clock or observer is being used for comparison. Imagine a clock held far above Earth. Suppose somehow that it could remain nearly stationary relative to a suitable Earth-centered reference frame instead of orbiting rapidly. Because that clock is farther from Earth's mass, it sits at a higher gravitational potential than a similar clock on the surface. Its gravitational time dilation is weaker. So relative to the surface clock, the higher clock runs faster. This already reveals why the title needs qualification. A clock can be in space and accumulate more time than a clock on Earth. Now change the situation. Instead of holding the clock nearly stationary, place it in a fast orbit. Its greater altitude still makes it run faster through the gravitational effect. But its orbital motion creates velocity time dilation. That works in the opposite direction. If the orbital speed is high enough, the slowing caused by motion can outweigh the speeding caused by weaker gravity. This is what happens to astronauts in low Earth orbit. The International Space Station travels around Earth at roughly 7.7 kilometers per second. At the same time, it remains only a few hundred kilometers above the surface. Its altitude reduces gravitational time dilation slightly, so clocks aboard the station tend to run faster than clocks below for that reason alone. But the station's orbital velocity produces a larger special relativistic effect in the opposite direction. Overall, astronauts aboard the International Space Station accumulate slightly less time than people who remain on Earth. The difference is tiny. After months in orbit, it amounts to only a small fraction of a second. Still, it is real. Now imagine a very different journey. A spacecraft travels far from Earth, but does so at a relatively low speed. As it climbs away from Earth's gravitational well, its clock can run faster than one remaining at the surface. The farther it travels, the weaker Earth's contribution becomes. If motion remains modest, the gravitational effect can dominate. But suppose another spacecraft races through deep space at an enormous fraction of the speed of light. Earth's gravity may be almost irrelevant there, yet the velocity time dilation could be extreme. That spacecraft's clock could accumulate much less time than a clock moving slowly elsewhere. So deep space is not a special slow time zone. A slow clock far from gravity can run comparatively fast. A fast clock far from gravity can run comparatively slow. The path matters. This also helps clear up another common misunderstanding. Astronauts in orbit feel weightless. It is easy to interpret that as meaning there is no gravity where they are. But there is plenty of gravity in low Earth orbit. At the altitude of the International Space Station, Earth's gravitational pull is still a large fraction of what it is at the surface. Astronauts float because the spacecraft and everything inside it are falling together. Orbit is continuous free fall. The station is moving sideways so quickly that as it falls towards Earth, the curved surface of the planet falls away beneath it. The result is a path around Earth rather than a collision with the ground. So feeling weightless does not mean escaping gravity. A person can experience no support force at all and still be travelling through strongly curved space-time. Their clock can still accumulate time differently from clocks elsewhere. This is because proper time does not depend on how heavy or weightless someone feels. It depends on the world line they follow through space-time. A freely falling astronaut can feel perfectly relaxed while their clock slowly drifts out of synchronization with a clock on Earth. No force needs to be felt for the difference to exist. There is another piece of language that needs care. When we say one clock runs faster or another runs slower, we must always ask one simple question. Compared with what? Relativity does not provide one universal clock against which every other clock can be judged. Instead, comparisons are made between particular observers or within particular coordinate systems. A clock on Earth's surface may run more slowly than one high above it because of gravity. That same high clock may run more slowly than another clock because it is moving rapidly. There is no single absolute answer to the question of whether a clock is running slowly. The comparison must be specified. This becomes important because Earth itself is moving. A person standing apparently still on the ground is rotating with Earth. Earth is orbiting the Sun. The Sun is moving through the Milky Way, and the Milky Way itself is moving relative to other galaxies and the wider distribution of matter in the universe. None of these motions reveals an experimentally preferred state of absolute rest. There is no known cosmic platform that can be labelled truly stationary, while everything else moves around it. In practical calculations, however, physicists and engineers still need useful reference systems. For problems involving satellites, one convenient choice is an Earth-centered coordinate system. That does not mean Earth is physically privileged. It simply makes the calculations easier. A different problem might be described using a frame centered on the Sun. Another might use a frame moving with a spacecraft. The underlying physics remains the same when the transformations are handled correctly. This is where relativity stops being only an elegant idea and becomes an engineering requirement. Real satellite systems must account for velocity. They must account for gravitational potential. They must account for Earth's rotation. They must account for the time taken by signals to travel between orbit and the ground. And they must keep many clocks synchronized well enough for tiny timing errors not to become large position errors. So the question of whether time moves slower in space has no one-word answer. Sometimes it does, sometimes it does not. Move quickly enough, and motion makes your clock accumulate less time. Move higher in a gravitational field, and weaker gravity can make your clock accumulate more. In the real universe, both effects often occur together, and for satellites circling Earth, those tiny competing differences have to be calculated correctly every single day. One of the clearest examples of relativity working quietly in everyday life is satellite navigation. The global positioning system is a constellation of satellites orbiting Earth and continuously broadcasting extremely precise timing signals. A receiver on the ground, such as the one inside a phone, a car, or an aircraft, listens for those signals and uses them to work out its position. The basic idea is wonderfully simple. If you know exactly when a radio signal was sent and exactly when it arrived, then you know how long it spent travelling. Because radio waves move at the speed of light, that travel time can be converted into distance. A receiver does this with signals from several satellites at once. By comparing those distances, it can determine where it is on Earth. The difficulty is that light is extremely fast. A timing error of only a few billionths of a second can translate into a positional error of meters. So the clocks involved need to be extraordinarily precise. Each global positioning system satellite carries atomic clocks. The satellites orbit at an altitude of roughly 20,200 kilometers above Earth's surface. They travel at around 3.9 kilometers per second and complete an orbit in close to 12 hours. At that speed and altitude, both special relativity and general relativity matter, and once again, they push the clocks in opposite directions. The satellites are moving rapidly relative to clocks associated with Earth. Because of velocity time dilation, their motion causes the satellite clocks to run slightly more slowly. The effect amounts to roughly 7 millionths of a second per day. 7 millionths of a second does not sound like much. But for a system trying to determine location from signals moving at nearly 300,000 kilometers per second, it is enough to matter. Then gravity produces the opposite effect. The satellites are much farther from Earth's surface than clocks on the ground. They sit higher in Earth's gravitational potential, where gravitational time dilation is weaker. That causes their clocks to run faster. The gravitational effect is larger than the velocity effect. It contributes roughly 45 millionths of a second per day in the faster direction. Combine the two, motion slows the satellite clocks by about 7 millionths of a second per day. Weaker gravity speeds them up by about 45 millionths of a second per day. The result is a net difference of approximately 38 millionths of a second per day. Without correction, the satellite clocks would gradually drift ahead of clocks associated with Earth. 38 millionths of a second still sounds almost absurdly small. But multiply that timing error by the speed of a light, and the resulting navigation error would grow rapidly. After only a day, the accumulated positional error could become many kilometers. A navigation system allowed to drift like that would not remain particularly useful for long. So relativity is built into the system from the beginning. The frequencies of the satellite clocks are adjusted before launch so that once the satellites reach their operational orbits, their ticking rates match the coordinate time used by the system as intended. But that is not the end of the problem. Real satellite orbits are not perfect circles. They have slight eccentricities. As a satellite moves through different parts of its orbit, both its speed and its gravitational potential vary. That produces additional relativistic corrections. Atomic clocks also experience small amounts of ordinary clock drift. Signals travelling from orbit to the ground must pass through Earth's atmosphere, where the ionosphere and lower atmosphere can alter their propagation. The exact position of each satellite changes continuously. All of these effects must be modelled, measured and corrected. Earth's rotation introduces another complication. This is associated with the Sagnac effect, named after Georges Sagnac. Imagine sending light around a rotating platform in opposite directions. Because the platform rotates while the light is travelling, the two beams do not return after exactly the same travel time. Earth is also a rotating platform. A satellite sends a signal towards a receiver that is moving with the rotating surface below. During the brief time the radio signal travels from orbit to Earth, the receiver changes position. So accurate satellite navigation must account for Earth's rotation when calculating signal travel times. This is another reminder that there is no single simple clock hanging over the planet. Timing depends on motion, position, and the coordinate system being used. The global positioning system is operated by the United States Space Force, but it is not the only satellite navigation network. Other constellations, including Europe's Galileo system, Russia's Global Navigation Satellite System, and China's Beidou Navigation Satellite System, rely on the same broad relativistic principles. Any satellite navigation system using precise clocks in orbit must deal with the fact that those clocks do not naturally tick at exactly the same rate as clocks on the ground. It is sometimes said that every time a navigation app works, it proves Albert Einstein was right. That is a little too neat. Special relativity and general relativity were tested independently in many different experiments long before modern satellite navigation became part of everyday life. A phone finding a restaurant is not a fresh experimental proof of relativity, but the technology does depend on relativistic physics being correct. If the relativistic corrections were deliberately removed, the system's accuracy would deteriorate very quickly, and that makes satellite navigation a useful example of how deeply these ideas have entered practical engineering. Time is no longer treated as one universal quantity shared equally between Earth and orbit. Engineers have to model how clocks behave at different speeds. They have to model how clocks behave at different gravitational potentials. They have to account for Earth's rotation, orbital motion, atmospheric signal delays, and clock synchronization. All so that a receiver can work out where it is. The strange physics of space-time has become part of the background machinery of ordinary life. A century after Albert Einstein changed our understanding of time, satellites circling thousands of kilometers above us quietly make those corrections every day. Astronauts really do return from space having aged slightly less than people who remained on Earth. The difference is not large enough to notice in a mirror. Nobody comes home from orbit looking mysteriously younger, but measured with sufficiently precise clocks, the effect is real. The International Space Station provides a good example. It circles Earth at an altitude of roughly 400 kilometers and travels at around 7.7 kilometers per second. That is close to 28,000 kilometers per hour. At that speed, special relativity becomes measurable. The station's motion causes its clocks, and everything travelling alongside them, to accumulate slightly less time than comparable clocks on Earth. But gravity complicates the picture. At an altitude of around 400 kilometers, the International Space Station is farther from the centre of Earth than people standing on the surface. Earth's gravitational potential is therefore slightly higher there. According to general relativity, that tends to make clocks aboard the station run a little faster than clocks below, so the astronauts experience the same competition that affects satellites. Their speed makes their clocks run slower. Their altitude makes their clocks run faster. For the International Space Station, the velocity effect is larger. The net result is that astronauts in low Earth orbit accumulates slightly less proper time than people who remain on the ground. Over a mission lasting several months, the difference is typically only a few thousandths of a second. It is a very small journey into the future, but it is still a journey of a kind. Cosmonaut Sergei Krikalev is sometimes mentioned in this context because he spent a total of more than 800 days in space across several missions. His cumulative relativistic age difference compared with someone remaining on Earth amounts only to a few hundredths of a second. So it would be rather generous to describe him as a dramatic time traveller. Still, the principle is exactly the same one that becomes much more striking at higher speeds. Everyone moves into the future at the normal rate of their own proper time. A person never feels their own clock becoming slow. Relativistic travel changes something more subtle. It changes how much time can pass elsewhere between two moments when travellers separate and later meet again. Imagine leaving Earth aboard an interstellar spacecraft. Suppose the spacecraft could somehow accelerate to 90% of the speed of light. At that velocity, time dilation becomes substantial. Imagine travelling towards a star that lies 10 light-years away according to observers on Earth. Ignoring the periods of acceleration and deceleration, Earthbound observers would say that the outward journey takes a little over 11 years. But the travellers aboard the spacecraft would experience considerably less time. At 90% of light speed, their Lorentz factor is a little above 2. So while more than 11 years pass in Earth's frame, the travellers experience only around 5 years. Nothing aboard the spacecraft feels slowed. Meals are eaten normally. People sleep normally. Clocks continue ticking normally. The travellers simply accumulate fewer years between the same departure and arrival events. From their perspective, there is another way to describe why the journey takes less time. The distance has contracted. Length contraction reduces distances measured along the direction of motion. Earth observers say the spacecraft must cross 10 light-years. The travellers, moving rapidly relative to Earth and the destination, measure a shorter distance between them. So the Earthbound description says that the spacecraft's clocks run slowly. The traveller's description says the journey itself is shorter. Both agree on the departure. Both agree on the arrival. And if the spacecraft eventually returns to Earth, both agree that the travellers have aged less. Now increase the speed further. At 99% of the speed of light, the difference becomes much more dramatic. A journey lasting many decades according to Earth could contain only a fraction of that time for the people aboard the spacecraft. At still greater fractions of light speed, it becomes theoretically possible for travellers to cross enormous distances within a human lifetime, while centuries or longer pass elsewhere. That possibility comes directly from experimentally established relativity. The problem is not the physics of time dilation. The problem is building the spacecraft. Accelerating something as massive as a crewed vehicle to a significant fraction of the light speed would require an extraordinary amount of energy. And the faster the spacecraft becomes, the harder the next increase in speed becomes. The energy demand rises dramatically as light speed is approached. Propulsion would only be the beginning. At relativistic velocity, even tiny objects become dangerous. A grain of interstellar dust striking a spacecraft at an enormous fraction of light speed could release a tremendous amount of energy. Individual atoms and particles in the thin interstellar medium would arrive as intense radiation. Protecting a crew would require substantial shielding. That shielding would add mass. More mass would demand more energy to accelerate. Heat would also need to be removed. Space is cold in the everyday sense, but a high-energy spacecraft cannot simply throw unwanted heat away easily. Radiators would be required, and those too would add size and mass. Acceleration presents another limitation. A spacecraft could theoretically reach high velocity gently by accelerating for a long period. But any propulsion system capable of doing this would need to operate reliably for extraordinary durations. And arriving at the destination creates another inconvenient detail. You have to slow down. A spacecraft that spends enormous energy accelerating to relativistic speed cannot simply reach another star and stop. Deceleration requires another major change in momentum and potentially a comparable energy budget. So special relativity allows a form of travel into the future, but it does not make that travel easy, nor does it provide a known route into the past. A relativistic traveller can return to Earth and discover that more time has passed there than they personally experienced. That is entirely compatible with established physics, but the traveller has still moved forward through time throughout the journey. Nothing in ordinary velocity time dilation allows them to return to an event that happened before they departed. Ideas such as warp drives and traversable wormholes sometimes appear in discussions of faster-than-light travel or time travel. These are very different. Certain mathematical solutions of general relativity can contain unusual structures that resemble wormholes or regions of effectively faster-than-light motion. But no practical traversable wormhole has ever been observed. No warp drive has ever been built. Many proposed versions require forms of negative energy or exotic conditions whose physical feasibility remains highly uncertain. Time dilation needs no such speculation. It has been measured. There is, however, another way for a traveller to accumulate less time than distant observers. Instead of moving extremely fast, the traveller could enter a region where space-time is strongly curved by gravity. Near a very compact, massive object, gravitational time dilation can become enormous. A traveller might move relatively slowly compared with a nearby observer and still accumulate far less time than someone much farther away. Neutron stars already produce much stronger gravitational time dilation than Earth, but black holes take the effect to its extreme. Near a black hole, the relationship between distant clocks and local clocks can become so distorted that the tiny fractions of a second experienced by astronauts near Earth begin to seem almost insignificant. Velocity can separate two travellers in time, gravity can do the same, and close to an event horizon, the amount of time separating their experiences can become extraordinary. Black holes take gravitational time dilation into a regime far beyond anything found around Earth. A black hole is a region of space-time where gravity has become so intense that an event horizon forms. The event horizon is not a solid surface. It is a boundary in space-time. Once something crosses it, no signal travelling at or below the speed of light can return to the distant universe. The mathematics describing the simplest kind of black hole emerged very quickly after Albert Einstein completed the general theory of relativity. In 1916, Carl Schwarzschild found an exact solution to Einstein's field equations for the space-time outside a perfectly spherical, non-rotating mass. His solution revealed a particular radius associated with the mass of the object. This is now called the Schwarzschild radius. If a sufficient amount of mass is compressed inside that radius, an event horizon forms. For a black hole with the mass of the Sun, the Schwarzschild radius would be only about 3 kilometers. For a black hole 10 times the mass of the Sun, it would be roughly 30 kilometers. A supermassive black hole containing millions or billions of solar masses can have a horizon spanning millions or even billions of kilometers. It is important not to imagine the Schwarzschild radius as the outer edge of an ordinary solid object hidden behind a shell. The event horizon is part of the geometry of space-time itself, and that geometry has a dramatic effect on time. Imagine placing a clock outside a non-rotating black hole and somehow holding it at a fixed distance from the horizon. Now compare that clock with another clock very far away. The closer the first clock is held to the event horizon, the more slowly it runs relative to the distant clock. As the clock is lowered farther and farther, the difference becomes increasingly severe. Near the horizon, a short interval experienced by the nearby clock can correspond to a much longer interval measured far away. But there is an important physical catch. Holding something stationary near a black hole is not easy. A freely falling object naturally moves along a geodesic. To remain suspended at a fixed radius, a spacecraft would need to fire its engines continuously. The closer it approaches the horizon, the greater the required acceleration becomes. For an ideal, non-rotating black hole, the acceleration needed to hover at the event horizon would become unbounded. So no physical observer can remain stationary exactly on the horizon. The behavior of light makes the time difference visible. Imagine the hovering clock sending a light pulse outward, once every second according to its own local time. A distant observer receives those pulses. As the clock is lowered closer to the black hole, the outgoing light becomes increasingly redshifted. Its frequency becomes lower, its wavelength becomes longer, and the pulses arrive more widely separated in time. To the distant observer, the clock appears to be running increasingly slowly. A falling object produces a similar effect. If a spacecraft falls towards the horizon while continuing to transmit signals, a distant observer receives those signals at progressively lower frequencies. They become redder, dimmer, and farther apart. This is sometimes described by saying that the distant observer sees the falling object freeze at the horizon forever. That description is easy to misunderstand. In practice, the observer does not continue receiving a sharp image of the spacecraft sitting motionless at the horizon for eternity. The signals become increasingly delayed, red-shifted and weak. Eventually they become effectively undetectable. The object fades from view. Part of the confusion comes from the coordinates used to describe the black hole. In the original Schwarzschild coordinate system, an infalling object reaches the event horizon only after an infinite amount of Schwarzschild coordinate time. But that does not mean the traveller themselves requires an infinite amount of time to arrive there. The apparent singular behaviour at the horizon comes from the coordinate system. Other coordinates describe the same space-time without becoming pathological at that boundary. Arthur Eddington developed an early form of such coordinates, and David Finkelstein later clarified their physical interpretation. In coordinates of this kind, the event horizon is not an infinite time barrier for something falling inward. The traveller crosses it after a finite amount of proper time, and for the traveller, the horizon does not necessarily announce itself with any sudden local event. If the black hole is sufficiently large and the traveller is freely falling, crossing the horizon can be locally uneventful. There is no solid wall, no flash of light marking the boundary, no clock beside the traveller suddenly stopping. The traveller's heartbeat continues, their watch continues ticking, their local experiments continue behaving normally. What happens next depends strongly on the size of the black hole. A small stellar mass black hole can produce enormous tidal forces near its horizon. Tidal forces arise because gravity changes noticeably across the length of an extended object. The side of a person closer to the black hole is pulled differently from the side farther away. This difference can stretch the body along one direction and compress it along another. A sufficiently strong version of this process is often called spaghettification. For a supermassive black hole, however, the event horizon can be so large that the curvature changes much more gently across the size of a person. The tidal forces at the horizon itself may therefore be relatively modest. A traveller could cross before the stretching became catastrophic. This highlights an important distinction. Gravitational time dilation and tidal forces are not the same effect. Time dilation concerns the different amounts of proper time accumulated along different world lines. Tidal forces concern differences in gravitational influence across an extended region. One can be extreme while the other is locally mild. Once the traveller crosses the event horizon, however, the causal structure changes in a decisive way. Inside the horizon, every future directed path leads farther inward. The traveller can still send light signals. Locally, those signals move outward at the normal speed of light, but the geometry is such that even outward directed light cannot increase its distance enough to escape to the external universe. So a message transmitted after crossing the horizon can never reach a distant observer. This is why the event horizon is fundamentally a causal boundary. It separates events that can still influence the outside universe from events that cannot. There is another popular claim that also needs care. A traveller falling towards a black hole does not simply watch the entire infinite future of the universe unfold before crossing the horizon. Incoming light from the external universe can certainly be distorted and shifted. Depending on the trajectory, some distant processes may appear accelerated, but the traveller has only a finite amount of proper time before reaching the horizon, and later the interior. The changing geometry, the direction of incoming light, and the finite supply of signals all prevent the simple idea of watching eternity happen outside. Large differences in the elapsed time are still possible. In principle, a traveller who remains very close to a black hole for some period and then escapes could accumulate substantially less time than distant observers. But hovering extremely close to a horizon would require enormous acceleration. Stable orbits have their own limits. Radiation from surrounding matter can be intense, and real black holes are often rotating rather than perfectly described by the Schwarzschild solution. So the most dramatic scenarios quickly become physically difficult even when the underlying time dilation is completely real. The deeper lesson is that a black hole does not simply switch time off. Nothing locally reaches a magical state where time disappears. Instead, the geometry of space-time becomes so strongly curved that clocks following different paths can accumulate radically different amounts of proper time. Far away, one clock continues ticking. Near the horizon, another follows a very different path. And the growing separation between those two measures of time is written into the causal structure of space-time itself. Most black holes in the real universe are not expected to sit perfectly still. Stars rotate, gas clouds rotate, entire galaxies rotate. So when massive stars collapse or black holes grow by swallowing matter, they naturally inherit angular momentum. That means the simplest non-rotating black hole is only part of the story. A more realistic description came in 1963, when the New Zealand mathematician Roy Kerr discovered an exact solution to Albert Einstein's field equations describing a rotating black hole. The Kerr solution revealed a space-time far more complicated than the one surrounding a non-rotating black hole. Rotation does not simply cause the black hole itself to spin, it changes the geometry around it. A rotating mass drags the surrounding space-time along with it. This effect is called frame dragging. Far from the black hole, the effect is weak. But close to a rapidly rotating black hole, space-time itself becomes twisted strongly enough that an object cannot simply ignore the rotation. Nearby trajectories are pulled in the direction of the black hole's spin. It is important to be precise about what this means. The black hole is not grabbing objects with some invisible rotating atmosphere. The paths available through space-time are being altered by the rotation of the mass. Matter and light follow those paths. One of the strangest consequences is the existence of a region called the ergosphere. The ergosphere lies outside the event horizon. Inside this region, space-time is being dragged around so strongly that no physical observer can remain stationary relative to the distant universe. A spacecraft could still fire its engines, it could still move locally, but it could not simply hover in one place relative to distant stars. It would be forced to rotate in the same general direction as the black hole. The ergosphere and the event horizon are not the same boundary. That distinction matters. Crossing into the ergosphere does not prevent escape. A sufficiently capable spacecraft could, in principle, enter the ergosphere and later leave again. Crossing the event horizon is different. Once inside the horizon, no future directed path leads back to the distant universe. So the ergosphere marks the region where remaining stationary becomes impossible. The event horizon marks the boundary beyond which escape becomes impossible. Time near a rotating black hole is therefore influenced by more than gravity alone. Clock rates depend on the strength of the gravitational field. They depend on orbital velocity. They depend on the direction in which an object travels. And they depend on how rapidly the black hole itself is spinning. A spacecraft orbiting in the same direction as the black hole's rotation can experience a different space-time geometry from one attempting to orbit in the opposite direction. This becomes particularly important near the innermost stable circular orbit. The innermost stable circular orbit is the smallest radius at which matter can maintain a stable circular orbit around a black hole. For a non-rotating black hole, that location has one characteristic radius. For a rotating black hole, the answer depends on direction. An orbit moving in the same direction as the black hole's spin can remain stable much closer to the event horizon. An orbit moving against the rotation loses stability farther out. This allows matter in an accretion disk around a rapidly rotating black hole to approach much closer before plunging inward. That has major observational consequences. Gas in an accretion disk can move at an enormous fraction of the speed of light. At the same time, it sits deep inside the black hole's gravitational field, so the light emitted by that gas carries the effects of both motion and gravity. Gravitational redshift lowers the frequency of light escaping from deeper regions. The relativistic Doppler effect shifts light differently, depending on whether the emitting material is moving towards or away from us. Matter, approaching at relativistic speed, can appear brighter and shifted towards higher frequencies. Matter receding from us can appear dimmer and shifted towards lower frequencies. There is also relativistic beaming, which concentrates radiation in the direction of motion, and the curved space-time around the black hole bends the paths taken by the light itself. Photons emitted from the far side of an accretion disk can curve around the black hole and reach a distant telescope. Some light may circle part of the way around the black hole before escaping, so when astronomers study the region around a black hole, they are not seeing a simple flat picture of a glowing disk. They are seeing light that has been shifted, bent, delayed, amplified, and redirected by relativistic effects. This is one reason horizon-scale observations are so valuable. The Event Horizon Telescope collaboration has studied the environments surrounding two supermassive black holes in particular. One lies at the centre of the galaxy Messier 87. The other lies at the centre of the Milky Way and is known as Sagittarius A star. The famous images produced by the Event Horizon Telescope collaboration show bright emissions surrounding a dark central region known as the black hole shadow. They do not directly photograph time dilation. A telescope cannot simply take a picture of time moving slowly. What the observations reveal is matter and light behaving inside the strongly curved space-time predicted by general relativity. The size and structure of the shadow, the distribution of surrounding emission, and the behavior of nearby plasma can all be compared with models based on relativistic gravity. Even in such extreme surroundings, a freely falling observer does not feel their own time becoming sluggish. A clock carried by that observer continues ticking normally. Their thoughts continue normally. A local experiment performed inside a sufficiently small, freely falling laboratory still behaves in the familiar way. Time dilation becomes meaningful when the observer's clock is compared with another clock following a different world line. That distinction helps avoid one of the most persistent misleading phrases associated with black holes. Time does not simply stop at the event horizon. In certain coordinate systems used by distant observers, the horizon corresponds to an extreme stretching of coordinate time. But coordinate time is not the same thing as the proper time measured by the falling traveller. The traveller crosses the horizon after a finite amount of their own proper time. Their clock does not freeze. Their heartbeat does not stop because relativity has somehow switched time off. Different coordinate descriptions can assign very different times to the same events. Proper time is what the traveller actually measures along their own path. Beyond the horizon, however, the physics eventually reaches territory where our understanding becomes incomplete. Classical general relativity predicts that collapse continues inward towards a singularity. Near that predicted singularity, curvature becomes extreme, and the classical theory is expected to break down. A complete description would almost certainly require a quantum theory of gravity. No experimentally confirmed theory yet provides that final picture. This is where well-tested physics and unresolved physics must be kept separate. Time dilation outside black holes follows directly from general relativity, and is supported by the broader experimental success of the theory. Frame dragging has also been tested in weaker gravitational environments. The behaviour of matter and light around compact objects continues to provide further tests. But the ultimate nature of the singularity remains unknown. So does the full quantum description of the interior. Questions involving black hole information, quantum gravity, and the deepest structure of space-time remain active areas of theoretical research. The unknowns are fascinating, but they do not undo what has already been established. Motion changes elapsed time. Gravity changes elapsed time. Rotation can twist space-time and alter the paths available to matter and light. And near a black hole, all of these effects can become extreme at once. The deeper lesson remains surprisingly simple. Time is not measured by one clock belonging to the universe as a whole. It is measured along a path. Change the path through motion. Place it deeper inside curved space-time. Carry it close to a rapidly rotating black hole, and the amount of time contained along that journey can change with it. Time can move more slowly for a traveller in space. But space itself is not what causes the difference. What matters is how fast the traveller is moving, how strong the surrounding gravitational field is, and which path through space-time is being compared with another. That is a very different picture from the one Isaac Newton gave us. In Newton's universe, time was absolute. It flowed at the same rate everywhere, quietly and independently, while planets moved, objects fell, and clocks simply tried to keep up. Albert Einstein replaced that universal background with something far more subtle. In special relativity, observers moving relative to one another do not have to agree on distances, durations, or which distant events are happening at the same time. The constancy of the speed of light forces space and time to adjust together. The simple light clock makes this visible. If light must travel at the same speed for every inertial observer, then a moving clock cannot tick at the same rate for everyone. That is velocity-time dilation. And because simultaneity is also relative, two observers moving steadily past one another can each describe the other's clock as running slowly without creating a contradiction. They are not comparing the same distant moments. The cleanest way to describe what each observer actually experiences is proper time. Proper time is the amount of elapsed time recorded along a particular world line through space-time. Different paths can contain different amounts. That is why the twin paradox has a definite answer. The twin who travels away and returns follows a different world line from the twin who remains on Earth. When they meet again, the traveller has accumulated less proper time. The clocks disagree because the journeys were different, and this is not merely an effect that exists inside thought experiments. Atmospheric muons survive long enough to reach Earth because of relativistic motion. Particles inside accelerators live longer in the laboratory frame than their rest frame lifetimes would suggest. Atomic clocks carried aboard aircraft return with measurable differences. Modern optical clocks can detect changes in ticking rate, caused by surprisingly small differences in height. Gravity adds another layer. General relativity tells us that clocks deeper in a gravitational field run more slowly relative to clocks at higher gravitational potential. So moving higher above Earth can actually make a clock run faster. Motion may push the other way. A rapidly orbiting astronaut experiences velocity-time dilation that tends to slow their clock, while weaker gravity at altitude tends to speed it up. Which effect wins depends on the particular journey. Satellite navigation systems have to calculate both. The global positioning system depends on atomic clocks in orbit, running at slightly different rates from clocks associated with Earth. Special relativity slows the satellite clocks because of their motion. General relativity speeds them up because they are higher in Earth's gravitational field. Both effects must be included if the system is going to tell you where you are with useful accuracy. For astronauts in low Earth orbit, the accumulated difference is tiny. Months in space may leave them only thousandths of a second younger than they otherwise would have been. But the same physics becomes far more dramatic at speeds approaching the speed of light. A sufficiently fast traveller could experience only years while decades passed on Earth. And near a black hole, gravitational time differences can become even more extreme. Signals sent outward from close to an event horizon arrive increasingly redshifted and delayed. To a distant observer, the nearby clock appears to slow dramatically. Yet a freely falling traveller does not feel their own time stop. Their clock continues ticking normally and crosses the event horizon after a finite amount of proper time. There is no single cosmic clock that occasionally breaks, stretches, or slows down. That picture was never really there. Instead, space-time allows different paths to contain different amounts of elapsed time. A person follows one world line, a spacecraft follows another, a particle, a planet, and a star each trace their own path as well. Every clock measures the time along the journey it actually takes, and perhaps that is the strangest lesson of all. Time is not something the universe hands out equally from one enormous clock in the background. It is local, it is physical, and it is woven inseparably into the shape of space-time itself.